I'm Adam.
I'm Max. I'm Isaac.
We'll be presenting our project to you today. So I'll start off and just kind of have an overview. So at the very beginning of our project, way back when, we just kind of came up with a bunch of different initial designs for both the external and internal. And we had way too many, probably like 15 each. We had to cut it down a lot. So what we did was we created like a preliminary decision matrix, created on a scale of -1 to 1 without any weighting. And then the designs that advanced past that stage got put into this decision matrix. And so we used a scale of 1 to 5, and we included weights. And we did this for both the external and the internal. And then the red ones are just ones that got eliminated in this round. And so this is just kind of to show you like what the different categories were and what the different weights are. And so like these percentages seem really random, and the way that we got those was based off of this. So energy and manufacturing were our two biggest concerns with the project. We wanted to make sure that our device would actually be able to pump and move as much as we wanted it to, but we also had to be able to make it. And so within those two, like these, the energy efficiency and output fell under like the energy category, and then the other three fell under the manufacturing category. And so like if you go back to the previous slide, like that's how we sort of ranked everything. And so once again, if you looked at a lot of our designs, they were all usually like within 5% of each other, which we felt was too close to like just determine based off of that one matrix. So we wanted to do a little bit more. So instead of looking at some of the other factors, we just looked at energy and manufacturing only. So these were the four for the external. These were our top two choices, and we ended up going with the foot pedal and flywheel, and we'll talk about that decision a little more later. And then for the internal portion, we did the same process. We were choosing between the air-driven dual piston and the cylindrical compressive diaphragm model, and then we ended up going with the air-driven dual piston. So that was our final selection for the internal process. And the reason why we didn't choose cylindrical expansive, compressive, even though it seemed to score a little bit better, was once we like actually looked at the design, we realized that instead of the initial idea on the left, it was going to be a little more like the right, and it was going to be a lot more complicated than we thought it would be originally. Like these three things, we realized we would have to have air or water or whatever fluid we were going to use coming in from different directions, and it wouldn't be enough just to come in from one port. And we realized it was going to be a lot harder to make than we thought, so that's why we went with the other option. And so this was our actual final design for the internal portion. This is kind of a long way from the air-driven dual piston, so we'll talk a little bit more about how we made that jump. But so the internal portion in the end was designed to have a capacity of about 220 cc's, and the reason for that was because that's what our external was aiming for, and since we were using an inelastic materials and incompressible fluid, we wanted to make sure that the amount of fluid being pumped by the driver would also be moved by the internal portion. So those are the top and the bottom of the shells. And then we also just had to make sure that we fit the anatomical specifications, so the ones that were on the master specs draft, and then also we had to make sure that our parts like would fit over the valves that we chose and things like that. So this is just showing all the different parts aside from like the diaphragm for our internal portion. And then this part down here was where the fluid where we pumped would go, and then this is a one-way valve and then one-way valve, so that's how fluid would enter and exit. And then this is a little animation. Oh, that didn't work. Just how you put it together. And so we used a lot of different materials and adhesives to kind of seal ours. This was the end product, which I think you guys all saw when we tested it in class. And it looks kind of ugly because we wanted to make sure that it wouldn't fall apart. So we used caulk or underwater sealant, we used hot glue, acetone to melt other PLA parts to try to keep it together. And then in the future, we obviously would use different materials. We wouldn't 3D print it. So I think that would take care of a lot of our issues. Like during the testing, one of our things snapped because it was too thin, and if we had used other materials, hopefully that wouldn't have happened. And then also using different material would help it reach like biocompatibility and sterilization standards. So we obviously wouldn't be using like some of the caulk and things that we did. And then also in the future we would want to actually test this. This wouldn't just be for biocompatibility. We also want to test out some other things and see the effects that it has. So for our system, we pretty much just had like one chamber, and we want to see how like that affects blood pressure and things like that. So I'll hand it up to Adam now.
So a lot of my work came in with doing a shakedown for valves and for the diaphragm. So for the valves, what I did testing, basically what's important on this slide is that we've got a relative resistance value, which is the flow, just the free flow without a valve over the flow through the valve, whether it's open or closed. And then there's a percentage flow value, which is flow open minus flow closed all over flow open. And so what that gave us was resistance values for the valve when it's in its closed position and resistance values for when it's in its open position. And it gave us a percentage flow. And it was very clearly that the ball valves were winning out. And I tried two different ball valves, ABS ball valve and a PLA SLA composite ball valve. This circuit drawing right here is just to illustrate why all we needed to really test was the resistance, because these two valves would be in parallel. So if we have a uniformly defined resistance value, then the pressure differential from here to here would be the same pressure differential, or it would be this, yeah, the same pressure differential. And so we would have going to closed, we'd have an output current and an output current for open, and then once the pressure differential switched to the other direction, this valve would switch and this valve would switch. And so all we needed was a universally defined resistance value, and then this should have been the percentage flow between valve closed and valve open. So the valve was designed for minimum flow, or for maximum flow while open and minimum flow while closed. This was done for closed. It was done with a rubber gasket that was 3D printed with the SLA rubber. And then for maximum flow open, the ball valve was able to translate, or the ball was able to translate all the way up to having a distance from here to here, from the bottom of the opening to the ball that was as big as the opening itself, so that the entire flow would be able to flow through the valve. So ABS showed higher flow, but we chose to use PLA SLA composite due to the preference of our manufacturers to maintain good relations, manufacturer being Josh Brown. So it was realized that the PLA balls float, so they were replaced with SLA balls, because having our balls float then depends on the orientation of our heart, which is not ideal. So then the diaphragm, that was everything for the valve. So the diaphragm was designed to avoid elastic materials, because we didn't think that we had access to good elastic materials that were durable. So shakedown for the diaphragm consisted of various bonding tests and basic construction of diaphragms. It was determined that we could get a good seal and with like the polyethylene bonding to itself, and then with bonding to other parts, we figured we'd be able to design around those. We had a couple ideas in mind, which you'll see later on. It was determined from shakedown that we would be able to design our goal was to design a diaphragm that had a peak and a trough that had equally low tension. Again, we're working with inelastic materials, and we have an incompressible fluid, so we want each of these to have a similarly low tension, because we don't want it to stretch. We had various tooling pieces. For the external is basically a mold and then an ironing press. Internal was a mold and then 2 ironing presses, because there were more contours on the inner diaphragm. So the external piston was attached to the external piston diaphragm was attached to the piston itself, and then this ring. And so this was to allow connection to the cap of the piston later on, much easier. And so, as you can see here, so the ring would attach to the cap right there, and that allowed us to, while we were manufacturing it, to caulk the internal surfaces and seal them effectively, or attempt to. The volume moved by the external portion had to be less than the volume moved by the internal. The volume possibly moved by the internal. Kim mentioned this earlier, but again, we have an incompressible fluid. We have an inelastic material, so therefore, whatever we move on the external side, since that's our driving side, has to be less than whatever is possibly moved by the cycling of the internal diaphragm. That's really important, otherwise our diaphragm would be under a lot of pressure and we would likely fail. Or it would stretch and then we end up failing. So caulk in both cases was assisted by this small caulk tool, which came in handy a couple times for difficult to reach places, such as the internal edge of the diaphragm, so we could go through holes and then go around and kind of flex it around a little bit to get more translation. The primary limiting failure was the ring connection on the external diaphragm. As you can see right here, that's where it leaked, allowed air in, and then we had a problem. So this is an avoidable material failure. A solution that we have is basically our piston connection worked great. Perfect seal, no problems, never had, after we did it and then after we tested it, no doubts about it, and then through the entire testing, no problems. So we would mimic this design by having an inner ring as well as an outer ring, and that way the diaphragm would be compressed about the inner ring, and it would be attached by screws through the diaphragm, and then caulked and rubber cemented on the meeting points between the polyethylene and the PLA. But again, we'd have different materials, so it would likely change moderately, but that would be a good sealing design. Though the internal did not fail, we suspected that there may have been leaks in between the diaphragm and the 2 halves going between chambers, and so because of that, we would seek a similar redesign here as well.
So then my part in the project was a lot of the research behind the piston as well, because we were going to use the piston for the internal and the external. But the problem was I was doing a lot of research, but a lot of pistons aren't waterproof or airtight, because if it's internal, absolutely no water or whatever driver we're using cannot be mixed with the blood. And the gaskets or the O-rings that existing hydraulic pistons have would definitely eat up a lot of the energy that we would be putting out due to the friction. And once it's inside the body, it would definitely not be easy to replace those gaskets and O-rings for repair. And so this was actually our first design. It had a conical bag that attached to the top and attached to this free piston. But what we changed about this design, later we realized, wait, there's the same pressure differential on either side of the bag. So, hey, we can get rid of this piston because it's no longer needed. And so it had 2 or 3 plastic rings that had rubber bands attached to them. And so we had our conical bag more or less in the same that volume and not touching these guides on the outside of the piston. So here's the completed assembly of the external piston. As Adam was saying, there's the cap and the ring, the piston head, and these ball bearing clips in the casing. Further, we're going to talk about the ball bearing clips. So here's a more detailed drawing of the ball bearing clips. They're pretty complex as well as simple they are. They definitely, it was a pain to have the tolerancing with these ball bearings be with these clips because it can be too tight so that the ball bearings couldn't be freely rotating, or too loose in that the ball bearings pop out while in use. And so we found with Josh Park the tolerancing for these ball bearings to be around 5%. And more importantly, this angle is about 15 degrees, or meaning about 80% of the ball should be covered or encased by the plastic. We later found during, like halfway through our project, I messed up and put these same casing radius and piston head radius and cap radius to all be the same because I was doing a revolve in SolidWorks. And so this actually turned out to be better in our case because we did a little post-processing, including filing and using acetone, and that made it really nice fit and smooth on. And it's really important that you kind of keep the 0 to 2.5% tolerancing, because with smaller parts under a ½ inch, you really don't have much plastic to do with, and it's way easier to have a lot more than have less because you measure twice, cut once. And so it's just kind of our effort to make the PLA process more of a science and not really an art. And so the other area that I struggled with was the barb connections. We had the two tubes that we bought. We bought a firmer tube for our external to internal because of its chemical resistance and other things like that. But the soft tube was given to us. And so what we found to be best for the softer tubes, the OD of the barb nozzle should match the internal diameter of the tube, while for the firm tube, while it's way less flexible, it should match the centroid of the barb triangle, should match the actually internal diameter of the tube. So again, the centroid, kind of like right here, for the firmer tube should be about the internal radius of the tube, while for the external, it should be here and here because it can go around the barb a lot more easier. And so here's just the math for it. And so that to be about the same for our barb in this case. And then the other tricky part was finding this horizontal distance. How much should the barb extrude away from the barb cylindrical body? And so we found that to be about 1/10. It can change for the flexibility of the tube, but it's still kind of an art at this point, but we found this general correlation to help. So a couple slide validations and redesigns that we would do in the future design. We do not think this, for some reason, we're dealing with water as our driving fluid, so it would have been wise to choose stainless steel or some other metal that wouldn't rust for obvious reasons. It didn't have a strong effect, but we believe after a while being in use, it would have definitely made a difference. And the shaft infill was about 30%, but we obviously realized after some testing that was not enough, especially for the shaft. We probably would have put a collar or a large fillet where the shaft meets the body piston right there just to give it some more support. And then the other thing, we could have gotten rid of the ball bearing clips themselves once we found the actual design, because we did the ball bearing clips, so we didn't have to reprint the same case. And so we could easily integrate them into the case design and then actually cut out and save some material by reducing the outer edge of the piston casing.
So, like Kim mentioned way at the beginning, we chose for our external driver a foot pedal with a flywheel. We chose the flywheel because we wanted a way to try and store and build up a little momentum, which would help maintain the pumping output for a longer period of time. And we decided that the foot pedal is also a little bit easier to operate for long periods of time than just using your arms. So all the drawings you've seen were made using this template. I Googled around and made a template in SolidWorks that we then used for our title block. I tried to mimic the title block at my internship. It's got good information. A lot of it we didn't use, but we'll talk about that later if we have time. So back to our flywheel. We decided that the critical component of the flywheel was the connection between the foot pedal and the axle. So that's what we did in our shakedown. We printed a flexible cylinder that we then tried to spin with other PLA printed parts. And it did okay, but then when we looked at the moment arm from basically the diameter of the axle versus the diameter of the flywheel, we thought it would be much more efficient to just use the 6-inch moment arm with your hand instead of trying to spin based off of a 1/4-inch moment arm using your foot. So we abandoned the foot pedal. So after Max finished finalizing the dimensions for the external cylinder, we hashed out all the dimensions for the external portion. This is the CAD of what it ended up looking like. Obviously there are a lot of parts. It is actually kind of a drawback. And there's a lot of places for tolerancing issues, a lot of places for things to break. So this is the base. We had a lot of issues with that, trying to get it to print because there was so much surface area in contact with the build platform that it would warp a lot. Had a couple failed prints. The one that finally did work is still not very flat, and the clearances are a little iffy. And then here's the front support and the back support. We ended up creating 2 bearings. Yeah, creating 2 bearings for this. We ended up gluing them to the supports. This wasn't the original plan, but once we figured out how much force it would take to actually pump the fluid, we needed stronger connections in our assembly for the flywheel to hold it down so it wouldn't actually lift itself instead of pushing the water. We also had a lot of tolerancing issues with the bearings. We got one pretty well done, but then our second bearing still has a lot of play, and it caused our flywheel to tilt down and basically bump into the front support, and so we couldn't use that for our final test. And so in designing the flywheel, we attempted to maximize the moment of inertia to get the highest angular momentum possible. To do this, we cut out a large number of small pockets around the outer edge, and we then filled those with iron filings. We had quite an adventure with this because we based all of our calculations on pure iron, which has a density of almost 8 grams per cubic centimeter. And this was our target weight. Our target weight was around 7 pounds. And so we had the volume, assuming the density was 8 grams per cubic centimeter. What we forgot was that iron oxidizing is an exothermic reaction and does not stop even when you are not looking at it. And our iron filings were actually mostly iron 3 oxide, which has a density of about 5 grams per cubic centimeter. So even filling all of the pockets all the way to the top, we still ended up almost 30% short of our target weight on the flywheel. So we had to compensate for that by adjusting the way we were going to seal the pockets. Initially, we had these little square pieces that we would glue inside so the top edge would be flush. But instead, we had to use scrap parts and a lot of hot glue. And so it doesn't look very good. So here's the final bill of materials for our external portion. So this is how we glued the bearing into the back support, mostly on the back face, and then we pressed it down so there would be more than one area of contact taking the force. The assembly of the bearing, this front bearing is the one that we had all the trouble with. It ended up with a lot of play vertically, and that was just difficulties tolerancing. Like Max said, making the ball bearings fit properly in PLA printed parts is difficult. So here's the connection of the cylinder to the flywheel. This one and the next one. Yeah, so here we originally used PLA pins for the connection. We found out that under high shear stress, they break very easily. So we then switched to a high toughness SLA printed part. But we found out after we printed them that high toughness materials don't, or at least this particular material, did not have very high stiffness, which was also a requirement. So, that's this slide. So we ended up having to abandon the printed parts altogether and repurpose some pins we found at Harbor Freight. And then, in the end, the clearance issues with the flywheel kept us from using it at all, so we had to switch to a simple handle. Some other issues we had with clearance were because of how we had to change the way we sealed the iron filings in, when the flywheel spun, it clipped the front support a lot, which meant it did not spin very well and was also slowly breaking down the seal on those pockets, and then we were going to dump iron filings everywhere, which would not be good. So we ended up using Josh's heat gun to heat the plastic till it was flexible and then just press it down, which worked. We're not sure how it affected the overall strength because we haven't tested that, but it worked for this case. And then the clearance for the tube, we overestimated the bend radius when we were purchasing the tube, and the height we left the cylinder on the rack is not high enough for it to bend on a surface, so it has to be overhanging edge. So we would change that by probably changing the tube that we use, because we are only using water instead of, we were initially thinking we might end up using oil, which would take a special tubing. And then, so in spite of all of our tolerancing and sealing problems, we successfully pumped 0.8 liters in about 40 seconds. This comes out to about 1.2 liters per minute, which is quite a bit short of our goal of 5 liters per minute, but